Hi, this is Tarun. I'm here to give presentation on assignment 5, event handling and signaling. Now let us look at the objectives of the assignment. To learn the basic programming techniques for input devices in Linux kernel. Second, to learn event handling and signaling in Linux. And third, to develop program patterns for imprecise computation. Now let us look at the task 1. Use Linux signal handling mechanism setgem and longgem to demonstrate an example imprecise computation programming pattern in which executing computation will be terminated and the existing result are put out when we double click the right mouse button. So this is how I have done. I opened the mouse file, created one thread for creating the mouse event, that is double click. If we don't encounter double click event between the computation, then we get a precise value of variable v as 1 after many iterations and program terminates. If we encounter double click between computation, then through the use of setjump and longjump, the program control goes to signal handler where we print the imprecise value of v as calculated in the last iteration. Let me show the working of the program. This is my mouse click event. This is how I am checking the double click. I'm checking between the first click release event and the second click event. So if it is less than 200 milliseconds, then it's a double click. If it is greater than 200 milliseconds, it's not a double click. Initially, I am opening the mouse file, then initially j is set to 0. So it goes into the while loop, the j is equal to 0. Then it increments the I, then the value of v converges to 1. If there is a mouse event, that is g mouse event is equal to 1, then there is a long jump that program control transfers to set jump buff. Then the value of j becomes 1, it goes into the while loop again. Then this condition is false, it goes here, raise sig user 1, the signal arrives, it goes to the signal handler, it prints the imprecise value of v in the last iteration and terminates the program. Now let's look at the second assignment. In the task 2 of the assignment, you are requested to develop a program of several pieces of program to test whether the Linux signal facilities does precisely and to show the time that a signal handler associated with threads is executed in the following conditions. First, a thread is running. So this is how I have done. I have opened the mouse file, created two threads, one for checking the mouse event, that is a double click event, and another for running the computation, that is incrementing a variable. If we don't encounter double click event, then the value of variable I initialized to 0 keeps on incrementing after every iteration. Once we encounter double click event, then the program control goes to signal handler where we print the value of variable I as calculated in the last iteration. So this is my program. I've opened the mouse file, created two threads, one for the mouse event, that is the double click event, and second for the computation. This is for my computation. It keeps on incrementing whenever the mouse event is equal to 1, then it goes to the signal handler where it prints the value of I in the last iteration and exits. So this is my running of the program. I get the last value of I in the last iteration, 17. Let's go to the assignment 2b. The thread is runnable, that is the thread running has a higher priority. So this is how I have done. I created two threads, one with a high priority and second with the low priority. When the high priority thread starts running, the low priority threads become runnable. When the signal arrives from the high priority threads for a low priority thread, then the signal priority then high priority threads comes to a runnable state and the low priority thread starts running and call the signal handler. So this is my program for task B. I've created two threads, function 1 and function 2. This is my high priority thread. I've set it to 1, and this is my low priority thread, set it to 90. So the high priority thread starts running first. So this is a high priority thread. After printing uh, thread 1 5 times, it calls the low priority and terminates. So this thread is called. I'll show the running of the program. So thread 2 starts running first, then it goes to a signal handler and then calls the thread 1. Now let's go to the task 2 3c. The thread is blocked by the semaphore, so this is how I have done. In this task we use a sig alarm signal. User enters the time after which the signal is to occur during runtime. We initialize the semaphore value to 0, so after encountering some wait function later, so the program comes to a standby as semaphore value is not greater than 1. After the time specified by the user, the signal occurs and program control goes to the signal handler. After executing the statements in the signal handler, the program control again come to the position it was before entering the signal handler, and we'll terminate the program using second signal. So this is how my program is. First I'm initializing the semaphore value to 0. Then it comes to a standby position because the semaphore value is 0. So after the specified time, the sig alarm arrives and it goes to the signal handler. It prints the statement, and after control C, the program terminates. Now let me show the running of the program. So it will wait for 3 seconds and the signal will arrive, and it will go to the signal handler. And now control C to exit the program. Now let's go to the task D. The thread is delayed, that is the nano sleep is called. So this is how I have done. When the in this task, a signal is created using sig alarm signal. The user enters the time after which the alarm is to occur. So as the program runs, it encounters nano sleep function. It sleeps for 10 seconds. Then after the time specified by the user, the signal occurs and the program control goes to a signal handler where it prints the time remaining for the sleep to complete and terminates the program. So this is how I've done. The user enters the time in seconds, which is less than 10 seconds. So I fix the time for which the program sleeps, that is 10 seconds. The nano sleep, it gives you 10 seconds. So after sleep, so in between the sleeping, the signal occurs and the program control goes to a signal handler where it prints the remaining time and it terminates. Now we come to the assignment 3. Where the assignment says the signal delivery to all the threads of the process. It says that in the Linux signal man page, it describes in a process director signal may be delivered to any one of the threads that does not currently have the signal blocked. If more than one of the threads has the signal unblocked, then the kernel chooses an arbitrary thread to which to deliver the signal. This suggests no matter how many threads have the signal unblocked, the signal will be delivered only to one arbitrary thread. Please write a test program to demonstrate the statement is correct for SIGIO, and then build a set of routines library that allow SIGIO signal being delivered to all the threads that are registered to receive the signal. So we'll foresee the test program for this statement. The test program to demonstrate the statement site for SIGIO. So in this task, the 4 threads are created, one for getting the single click event, another 3 threads. What happens in Linux is as soon as the signal arrives, it arbitrarily goes to one thread. Our goal of the task is to prove the previous statement. So what I've done in this program is, when a single left click happens, only one arbitrary thread starts to run. On another single click, two arbitrary threads starts to run. On another single click, Three arbitrary starts to run, and on the fourth leg the program terminates. So this is how I've done. These are my three threads, 1, 2 and 3. This is my signal handler. This is the thread for getting the single click event. Now I'm opening the mouse file over here. This I've done to prevent the SIG user from getting into the main thread, and I'm creating the 4 threads here. So whenever a mouse event happens, it calls a thread. So on every mouse click it calls another thread. So I'll show you the demonstration of the program, and on the fourth click it exits. So on the first click only one thread is active. When I click once more, only 2 threads are active. That is one, as you can see, it is 1 and 2 threads are active. On one more thread, 1, 2 and 3 threads are active, and on the fourth click the program terminates. So now the last part, I will show you how we build the library functions for the SIGIO signal being delivered to all the threads at the register to receive the signal. So in this task, six threads are created. What happens in Linux is, as soon as the signal arrives, it arbitrarily goes to one thread. Our assignment states are to create library functions such that once a signal SIGIO arrives, it doesn't go to one arbitrary thread but goes to all the threads that are registered. The threads that are registered by putting the value 1 in the array sigmas against the number. For example, if first and second threads are registered, the array would be sigmas 110000. SIGIO I'm generating by the movement of the mouse. So this is my program. So these are my 6 threads, 1, 2, 3, 4, 5 and 6. This is my signal handler. This is my sig mask. So now thread 1, 3, 5 and 6 are registered. This is my library function, which I am sending the total number of threads, the PID and the sig mask, that is the registered thread, area of the registered thread. This is my library header file. I've declared it and I've defined it over here. It gets the thread ID, sig mask and the number of threads. If it receives the value from one thread, it passes to all the registered thread. So I'm opening the mouse function here. I'm setting it for SIGIO. By doing this, I'm blocking the main thread from getting the SIGIO signal. So I'm creating all the threads. So now let me run the program. So when I move my mouse, I'll get the values. So as you can see, the signal arrives on thread 1, thread 3, thread 5 and thread 6 as they are registered. Thread 1, 3, 5 and 6 as they are registered. So that's it for the assignment 5. Thank you for watching.